Hi, everybody. Welcome back for the morning. We're very happy to have for our first talk today, Alexandre Stauffer from University of Bath, and he'll be talking about competing first passage percolation.
Thanks a lot, Jack, and the organizers for the invitation. Thanks, Jack, for pronouncing my first name correctly. So it's Alexandre in Portuguese. Good to catch that. So I slightly changed the title of my talk. So I'm going to talk about competing first passage percolation. So it's a model of competition of multiple type of first passage percolation. But my goal here is that this model, I want to talk about a particular model that turns out has been very useful to analyze other models. I'm going to try to give you this perspective. So let me start, before introducing the main model, talking about where this came from. So this came from the analysis of a model known as multi-particle diffusion limited aggregation, or MDLA for short. So let me define this model. So we take ZD, can be in any dimensions. Usually, I'm not going to consider dimension 1 for this talk. And I'm going to define a growing process which starts from the origin, initially occupies the origin, and it's black dot here, and it will grow over time. And then at each site that's not the origin, I'll flip a coin, right? And with probability mu, which is the parameter, I'll put a particle there, which is this red ball here. And with probability 1 minus mu, I leave the site vacant. And I do this in an IID fashion for each site but the origin. And then this is time 0, the process starts. And what happens is the particles, so the red balls, will just evolve at a simple exclusion process. Okay, so each particle has a Poisson clock. When the clock rings, the clock of this particle rings, it chooses one of its neighbors uniformly at random. For example, choose the left one, and then just go there. And there is the standard exclusion rule. If a particle chooses to jump on a site that's occupied by another particle, the jump is just suppressed, and the process evolves. Okay. But there is an additional feature that makes this process more complicated than simple exclusion, is that if a particle decides or expresses a wish to jump on a site that is occupied by the aggregate, this jump is also suppressed, but the particle gets aggregated. And aggregated means it's now part of the aggregate, it doesn't move anymore. It stays there forever. It's frozen there. Okay? So the aggregate is this black set of sites will grow over time as particles attach to its boundary. Okay. Good. So this process was introduced in 1980 by Rosenstock and Marquardt in a paper where they want to analyze a phenomenon in photography. And then in 1981, a very famous paper in physics by Witten and Sander introduced the DLA model that most of you probably heard about. And DLA model was introduced as a simplification of MDLA, because it was very difficult to simulate at that time a process with so many particles moving at the same time. So they decided to add particles one by one from infinity. Okay? So that's the DLA version. It's just a simplification of MDLA as Witten and Sander introduced. The funny thing is that after 1981, DLA really became very popular. It exploded in physics. So there are several articles about it. This paper is really highly cited, but people forgot of MDLA until 1984, when Foss reinvented MDLA, claiming that it was a more realistic version of DLA, even though DLA was a simplification of MDLA to start with. I mean, Witten and Sander cites, obviously, for the Stochastic Marquardt, so that shouldn't have been missed. But yeah, so but Foss was still important because it really popularized MDLA. After his paper, MDLA and several other variants of this type of process were studied in physics a lot. But still, in mathematics, we know very little about these guys. So what do we want to know about this? So I'm interested in the long time behavior of this process, and especially in two particular questions. I'd like to know whether there is positive speed of growth of the aggregate of the set of black sites, and by positive speed of growth, I mean something very modest. I just want that the radius of the aggregate, so AT is the aggregate, the sites occupied by the aggregate at time t. So I want the radius of this set, which is just the supremum of the L1 norm of the vertices that are contained in the set. I just want this to be bigger than a constant times t for all t large enough. So in other words, if I divide both sides by t, I just want the limit to be positive. I don't want, I'm not claiming, when I say positive speed in this talk, I'm not really referring to the limit existing, but just that it has positive limit. And so a more modest goal than usually in this conference. And then I'm interested also to know whether the aggregate forms a bulky set. And this will be precise when I state the result, but by bulky set, I really means it looks like a ball. It's never going to look like a ball because we have holes inside, but it looks like a ball in some sense. Okay. So that are the two questions I'm interested in this model. So let's start with some extreme case of the parameter mu, which is the density of particles. So mu is between 0 and 1. If mu is 0, I think we don't need to talk about this process. If mu is 1, then we have particles everywhere, right? All sides have a particle. Nothing happens because particles cannot jump, but still they can try to jump on the aggregate, at which time they get aggregated. So the aggregate still grows. But how does the aggregate grow? Oh, it grows when this particle decides to jump, which has some rate 1 over the number of neighbors. So it's exactly first passage percolation. So it's first passage percolation with exponential passage times. I don't care about the parameter of the exponential. That's first passage percolation. So it means obviously it has positive speed, right? It had a shape theorem. So it's really bulky. It's really a ball according to some norm. It's bulky in a very strong sense. Okay, but what happens when mu is smaller than 1? In particular, what happens when mu is much smaller than 1? So let me show you two pictures of simulations that I did on this process. Let's look at mu equals to 0.2. And the simulation shows a picture like this. So what I'm showing you are the sites occupied by the aggregate up to the point I stop the simulation. Different colors just mean different epochs of the simulation. And if you look from very far away, like Martin, you'll see like a kind of a shape appearing. But if you look here, like me and Jack, you can see inside that it has very delicate structure, very ramified and delicate structure. It doesn't really, in the microscopic sense, it doesn't really look like an actual bulky shape. And if you decrease mu, the situation gets even more stronger, more pronounced. If mu is 0.1, you see a shape like this appearing. So you see a very, really ramified fractal-like structure, if you like. And it's easy to convince oneself that once, say, these two arms, this one and this one here, they form, it's very difficult for particles to fill in this gap, right? Because a random walk particle that's moving like simple exclusion, so it's essentially like a random walk, it has to enter this gap without touching the two boundaries, otherwise it gets stuck there to fill it, the gap inside. Okay, but still a random process. So at some time, some brave particle would do it, but by that time you grow other arms around. That makes it even harder. So it's easy to convince oneself that this picture can be maintained. Yes.
You said it was ramified. You know what that? Can you explain what that?
So the question is whether I can explain what ramified means. And the question is no, it just looks like a painting structure. We know nothing about it, so I cannot really quantify what ramified means. But what I mean by it intuitively is just that it forms these branchings, right? These growing arms in every direction, right? Branching from this structure. That's what I mean by it. But I mean, nothing of this can be actually proved.
So you can't prove even that there exists some site that eventually all of its neighbors don't get occupied?
That's easy to prove.
Okay.
Right? These local holes is easy to prove because you can just look at a local event where when the aggregate gets there, particles will just go around and close it. This you can prove. But you cannot prove, for example, that you have these long fjords that go all the way. That you cannot prove. Even weaker results, weaker than this, we cannot prove. It's from the 1980. So after the survey, the book on first passage percolation, on the 50 years of first pass percolation, I thought, well, why not writing the 40 years of MDLA, right? But it will be a really short book, so better not. Okay, so what can we actually say about this? So first, why do physicists care about this? And the question is, there are several models in nature that forms this kind of structure, right? Process of bacteria when they grow in an environment with a lack of food, crystal growth, or this electric breakdown, or electrodeposition. There are several others. Actually, I even saw once in my kitchen when I was cooking, arising some MDLA. It really appears. So the physicists wanted to introduce a simple model that produces it and see what mechanism can produce it. And that was the goal of the paper in the 80s.
So you also see it in simulations that Martin Heiler shows in his talk when he simulates dendritic structure.
Yes, exactly. Dendritic is the word, and that's right. Those are different phenomena, though. Different mechanism of growth. And I think that both objects are very different. Okay, so what can we know about this? And actually, it's fair to say there are 2 papers about it. And not 3, 2, right? And I'm talking about dimensions 2 and higher. And the first paper is by myself and Vlada Sidorovicius from 3 years ago. And we show that there is a regime of positive speed of growth in dimensions 2 and higher. And what I mean by this is just that there exists a value of μ0 such that if the density is smaller than this, then the probability that the radius of the aggregate at time t is bigger than some constant t is positive. And this is for all t. Okay. This is not really the final story because you don't want it to be positive. You'd like to be 1 just by replacing the for all t for all large enough t. Right? But still, even if you put here for all large enough t, our result will just give this with positive probability. But we showed a little bit more. We also show that this forms a bulky behavior in this regime. So if the density is large enough, then if I look at the aggregate at time t, union of all the finite components of the complement of the aggregate, so I look at the aggregate and fill in the holes that the aggregate produces inside, then this set contains a ball of radius constant times t for all t with positive probability. That's what I mean by bulky. Okay, so the first result can actually be improved to probability 1, and this is a result of Alan's lie, actually in dimension 1, but his proof can be adapted to higher dimensions to show that the probability the radius of the aggregate is at least constant times t for all large enough t is actually 1. But his proof is really relies on 1 dimension, so it gives no information about the geometry of the aggregate. In particular, it doesn't say that it's bulky or not. And also here, maybe I forgot to write, this is for mu large enough. So we know nothing about small values of mu, absolutely nothing. There is no single result about it. So that's all the literature. 2 papers, as I promised. Dimension 1 is a little bit special. I have to change a little bit the model, and you can say more about it. But dimensions 2 and higher, that's it. Okay, so what I want to tell you is how we approach this model. How do we analyze this? And the reason I want to tell you this is because we introduced a new model, which is a competition of first passage percolation. It turns out to be very useful and can be, I believe, useful in analyzing other models. So let me introduce it. So that was all I want to say about MDLA for the moment. So is there any question about MDLA? Yeah.
Can you say anything about the boundary as u goes to 0? U goes to 1 and goes to
Yeah, we know nothing about anything about mu going to 0, actually. Absolutely nothing. We don't know whether it grows with speed. We don't know whether, even weaker question than what you ask, we don't know. Right? Okay, so we don't know what else I want to say. We don't know whether the complement of the set has points of constant distance to the origin. So we don't know anything. That's really open. So what was the question?
Yeah, it was the chat question was, do we know anything about a critical regime between dendritic and bulky behavior? You can.
Yeah, that's what we expect. So expect that there is a phase transition between a regime of small mu, where we have dendritic behavior, and a regime of large mu, where you look more like a first passage percolation in a random environment that's changing over time. That's what we expect. We expect it to be bulky for large mu and non-bulky for small mu. We expect to have, well, we can prove positive speed for large mu. We don't know whether for small mu there is positive speed or not. And this is a debate among people that have looked at this problem. But certainly simulation gets very slow. Just because for low mu, the aggregate sits there waiting these particles from far away that find their way to the aggregate. But we can't rule out that it has positive speed or not. And actually the conjecture is that it has positive speed for all mu. Okay. But let me also remark that we don't know this process is monotone. So we cannot really even say there is a phase transition of any kind. Okay. So it's not, we don't know whether it's monotone in mu. Yeah.
Can you go back to your picture?
Yes. This.
So in this picture, it doesn't look like holes are getting filled in. It looks like there are these long channels that are getting harder and harder to fill in. So can you talk about that compared with your result that seems to say the holes get maybe not filled in, but covered up? It looks like these holes are kind of going all the way, these channels are going all the way back to the origin, yes, without even getting covered up.
Yeah, that's right. So simulation suggests that to have these channels of fluids that straight all the way to near the origin, right? That's a conjecture. I can't prove anything about it. But if mu is larger than 1, then you don't have this because you have a bulky behavior. You know that these gaps will be closed eventually, and the process will continue growing.
Okay, so this is for a small enough mu that that result doesn't apply.
Yeah.
Okay, thanks.
So we can say that something like this, that the boundary will be sort of sparse and more sparse as mu decreases. Something like this is a conjecture?
The boundary, yes. Well, we can't say that. We can't prove that. That's
we can prove that by using the, picking specific points on the boundary, something like that.
That's actually the core of, if you can show that, right? If you could, okay, let me backtrack a bit. So it's easy to see that this set, the set occupied by the aggregate, will have density in the limit as a subset of ZD of at least mu. It cannot have a smaller density, otherwise the particles have disappeared somehow, right? So the density will be mu or higher. And now we have to understand whether it's higher, because if it's higher, it means the aggregate is stealing particles from the environment. It's denser than the environment of particles, and this will suggest speed 0 of growth, because then the distance between the boundary of the aggregate and the closest particle will grow over time. Okay? If you can show the density is actually mu, then there is some sustained, not self-similar, but there is some sustained density where you absorb particles, but you are moving forward, so you are reaching to fresh environment as you go. So you should have positive speed. Okay. So we don't know what the density of the boundary is, whether it goes to 0, we know nothing, but it's at the core of understanding whether it has positive speed or not. These questions are similar in some sense. Have more questions? No? Okay. So now let's move to first passage percolation. So now I'm going to introduce another model. Just forget MDLA for 1 second, no, for more than 1 second. And we're going to define a competing first passage percolation model, which has 2 types. FPP1 is the first type, and the second type is FP lambda. Sometimes I call it type 2 or type lambda. They're all the same. And the starting configuration is FP1 starts from the origin. It occupies the origin, while FP lambda starts from a collection of what I call seeds. And this is just IID with probability P on the ZD minus the origin. And now the parameter is P, just not to be confused with the mu. And the process starts at time 0 as follows. The seeds do not do anything. They just wait patiently for their time to act. Type 1 grows as first passage percolation of rate 1. So it's just exponential passage times of parameter 1. So it just starts growing. It occupies further and further sites until a moment where it expresses a wish to occupy a site that holds a seed. At this time, it does not occupy this site. This site, I say that the seed gets activated. And it's effectively occupied by the second type, by FP lambda. And from this moment on, this seed will start growing the second type, FP lambda, as a first passage percolation, but of rate lambda. That's why FP lambda. FP1, rate 1, FP lambda, rate lambda. And the two processes compete for space. Right? Each time a seed is about to be occupied by either type, could be type 1 or type lambda, it just gets activated, it gets occupied by type 2, and the process continues. Okay, so each site gets occupied by the type that gets to it first and never change type afterwards, just remains there. So the two processes compete for space. Okay. So a very simple, natural, let's say, first passage percolation with competition. And the main question I want to analyze is which types survive, and survive here doesn't simply mean grow indefinitely, as usually. What it means is survive means produce an infinite cluster. So I require that the set occupied by the type is connected, not that the whole set is connected, but it contains a connected set of infinite cardinality for the definition of survival. Okay, so type 1, obviously, if it grows indefinitely, it produces an infinite connected cluster. But type 2 could be composed of, it's always an infinite set. That's why I require the extra condition of being a cluster, because all the seeds will eventually be occupied by type 2. But it has to do more than this to survive. It has to have an infinite set of connected sites. Let me just mention that actually I don't distinguish clusters of seeds, cluster of type 2 growing from different seeds. For example, if this cluster grows here, here, and go around here all the way to the other side, I will consider all these things as a single cluster. Okay? And then there is also the question of whether there is coexistence in this model, which means whether both types simultaneously give rise to infinite clusters. Okay. So let's get rid of some trivial case. First, I'll keep here sometimes the two parameters of this model. So it's lambda, which is the rate of FP lambda. And note that if I increase lambda, I make FP lambda grow faster. So I kind of favor FP lambda. If I increase P is the density of the seeds. So I add more seeds. So I also favor FP lambda. So increasing either of the parameters favors FP lambda, decreasing favors FP1. And to a point where if I increase too much P, it becomes trivial. So if P is bigger than 1 minus PC site, C site's probability of site percolation on ZD, then if you just reorganize this, put P in the other side, you get 1 minus P is smaller than PC site, but 1 minus P is just the density of non-seeds. Non-seeds is the place where the type 1 can grow. If this is smaller than the critical probability for site percolation, type 1 is confined to a finite set at time 0. Okay, so it's trivial. Type 1 dies out, type 2 survive. We don't bother about this case. So we are restricting ourselves to P smaller than 1 minus PC site. Okay. So as I said, increasing either of the parameters should favor FP lambda. So the question is there monotonicity? So the standard way you would approach this to try to establish monotonicity would be to do a coupling, right? To take two configurations, maybe with the same initial configuration of seeds, but you add an extra seed in one of the process, and let the two evolve in a coupled way, aiming to show that the process with the extra seed has more type 2 sites. Well, let's suppose I add this seed here to one process and not to the other. And then until this process grows up to the way of activating these seeds, both processes I can couple them. I can couple all passage times so that they grow identically up to the point of activating this extra seed. Let's suppose type 1 gets here. So what happens is when the seed is activated, type 1 has to go around, right? So it gets a little bit of a local delay, as we expect, because we are adding the seeds, so it should favor type lambda. So type 1 gets delayed, which doesn't happen in the process without the seeds. But the issue is that because of the seed delay, further seeds that hang out along that direction maybe get activated later because of this delay that type 1 incurs here. They get activated later in the process with seeds. But this could be beneficial for type 1, because if it activates that seed later, by the time the seed is activated, maybe type 1 grew around here, is in a better position to attack the growth of that seed. So it's very easy to come up with the passage times and location of seeds so that adding a seed make you switch from a regime where type 1 dies out to a regime where type 1 survives. So adding a seed helps type 1. It's counterintuitive at first, but it's easy to convince yourself that it can really be done. It's so easy that actually I have a result that proves that there are graphs for which the probability that FPP1 survives is not a monotone function of P and lambda. So this is not a monotone process at all in generality. And so it can occur multiple phase transition in such graphs. And even though the graphs are designed to produce these counterexamples, they are not super weird because they are quasi-transitive graphs. So this process is a little bit funny. Even though the question on ZD, whether monotonicity holds, is still open. Right? And I believe it should be monotone. But well, without monotonicity, we cannot use it to prove anything. That's right. Yes. If lambda is bigger than 1, then the process is monotone.
Type survives, implying that there's exactly one type that survives. It seems like that's maybe obvious in dimension 2, but is that obvious in all dimensions that exactly one type is going to survive? It's
not obvious in any dimension but dimension 1. Okay. Yes. In dimension 1, of course, I don't consider it. Its process is trivial. But in dimension 2 and higher, yeah, whether there is coexistence, which is both types surviving simultaneously, is an interesting, very interesting question. And we're going to address this. More question? Okay, so we cannot use monotonicity. That's bad news. Okay, let me show quickly two simulations just to give you an idea of how this process looks like. And I'm going to take parameters very small. So I'm kind of trying to favor FPP1. So see, I'm taking P super small, 0.03. It's tiny. So very low density of seeds. And lambda is smaller than 1, but substantially. It's not like 0.999, 0.7. So FP1 is FP2, FP lambda is in a very bad shape, right? It's very small density of seeds, strictly is lower and substantially is lower than FP1. But the picture you see is this. So the colored ramified structure you see here are the sites occupied by FPP1 up to the point I stop the simulation. The white region here are the sites occupied by FP lambda. And the gray region are the sites not occupied, including non-activated seeds, by the time I stop the simulation. So even though these parameters are very modest and FP lambda seems in a very bad shape, it managed to conquer huge regions of the space. This is just to highlight a little bit how strong the dependence are in this process, because whenever a seed is activated and by random fluctuations just grows super quickly in the beginning, just upon activation, just there's a burst of growth, there is an advantage that it gets locally takes a long time for FP1 to go around and get over it. Because as FP1 go around, it has to face other seeds and has to dribble that fact until it managed to really surround and encapsulate the seed that got this burst of activity in the beginning. So these dependencies are super strong, and this is manifested well in this picture. So let me try to show you the opposite behavior. I'm going to take now lambda super small, and P will be quite large, actually. So let me show you what happens if P is very large, and even though 0.4 doesn't look like very large to you and to me, it is very large, because PC site is about 0.55 in ZD, in Z2, and we need P to be smaller than 1 minus PC site, so 1 minus PC site is 0.45. So I'm getting very close to the threshold here, 0.4. And lambda is tiny. And the picture you get is this. So the first thing you can note here is that the colors of the FP1 seems less bright than the previous picture. And this is because FP1 has this very dense set of seeds that has to go around. So it dribbles all this very packed set of seeds. So what you see here is a set occupied by FP1, but full of holes inside. Completely, there are seeds and small bursts of seeds, so it's very porous. In some place, FP lambda managed to block FP1 and grow this small, thin area around, right? But it's very thin because lambda is very small, so FP lambda grows very slowly. It seems like FP1 is in a better shape here, but actually a different kind of dependence arises in this setting. So these two settings are very different from one another. So the dependence that arises here, that if you look at this region, you have 2 points that are very close in Euclidean norm or L1 norm or whatever. So see, this point here is very close to this one in ZD, but they are actually occupied by very different epochs of the simulation. So this one is very in the beginning, is the first color, the black color, while this one is the very last color. So they're very close by, but they're all entered. They participate in the process in very different times. So we have this very strong dependence on the time at which regions are entered in this regime. Okay, so now before telling the results on this model, actually the model is called first passage percolation in a hostile environment. Yeah, that was Vada's idea. He was very creative in getting names to things. So that he suggested this name. So we call it FPPHE. And let's see how we use this model to analyze MDLA. Okay? And the idea, let's imagine MDLA in the model with high density, so mu close to 1. So let me give you an idea why this model is interesting. Let me try this here. So what we do is, let's tessellate. So this is MDLA. We tessellate, say, space into boxes. Okay. And then we look at a box of this space. Typically, if mu is very large, what you see inside the box is a packed set of particles. Right? There is particles everywhere here. This is all full of particles. Okay. So typically, most of the box will be like that because mu is very close to 1. So when the aggregate gets to this box, let's suppose the aggregate is red. If the aggregate is growing and gets to this box, because it's so full of particles here, the growth here will essentially be like first passage percolation. Right? So the aggregate managed to go conquer this region very quickly, because first passage percolation, we know the passage time is between 2 points of the box. As long as this continues to be packed all the time, it just grows the first passage percolation. So that's quick growth locally. And this we represent by the spread of FP1. FP1, once it gets a region, here we also have this dense set of particles, right? It's particles everywhere here. Then again, after we get here, the aggregate to get this region quickly. So if you look at this as a renormalized lattice, each of this box has a site of your of your lattice, you say once you get here, you quickly get there, and then you quickly get neighbors, and you keep going this in a random fashion, but no, it's like FP1 growing at rate 1, just growing. But at some points of a space, you will find regions that are just bad. For example, maybe this one is bad. And bad means you don't have this packed set of particles. You, by chance, you just got a region, say it has no particle inside. Suppose it's completely empty. And this is modeled by the seeds. Those are random places where when the process that's growing, in this case the aggregate, gets there, it just looks like, oh, I'm in trouble. I've just found a region where I don't have particles. And that's bad. Okay, what happens is when you find this region, because it has no particles, it affects nearby regions. Right? If I have lots of particles here, since these I have no particles, some particles, as the aggregate grows, they will start moving inside and you decrease the density of particles in this region. So maybe at the time the aggregate goes and gets there, this region is not to be as favorable as these ones. And this spread of effect of bad regions, we model as the growth of seeds. Right? When I activate a seed, when I discover this region, I activate it, and it spreads. And these models, they spread of how the type 2 grows. And actually, you can make this formal so that as long as you can show that these bad regions or the type 2 grows slower than type 1, and the seeds are not very dense, they are very low density of seeds, then you can show that this type 1, the aggregate, grows around it and get over each of these bad regions as it discovers. So there's a very rough idea on why FPPHE kind of models the way this process, this growth process, this MDLA behave. And actually, you can do this in more generality, to more models. And very recently, Duncan Doverne and Alan Sly used this FPPHE process that we introduced to analyze models of non-equilibrium spread of infection. So this approach seems very promising to analyze models where there is a front going that moves through typical good regions and leaves behind bad regions that it discovers. It could be an interesting model to analyze other models. So that was actually the main thing I want to convey in this talk. So let me now tell you what is known about FPPHE, because if you can't analyze FPPHE, of course, you cannot use it to analyze anything else. So I have two results to report. The first one is in the original paper with Vladas, and which we used to analyze MDLA, and we show the following, that for any lambda smaller than 1, and this was very important for us, for any lambda smaller than 1, if P is small enough, then FP1 survives with positive probability. And for this process, positive probability is the best you can hope for, because with positive probability, the origin is going to be surrounded by seeds, and that's over for FP1. And not only it survives, but actually it survives and kills FPP lambda with positive probability. So it means that every single seed of FPP lambda may grow a cluster, but this cluster will eventually be encapsulated by FP1, and FP1 gets rid of it and moves forward. And this was very important for this picture that I showed you. So you get rid of any bad region as it grows. And finally, we also show a bulky behavior. This is the same thing. This is the sites occupied by FP1, including the finite components of the complement. And this contains a ball of radius c times t for all t, so it has positive speed and is bulky. Okay. So that's the picture when p is small. So essentially, if I look at a phase diagram, like here, I have p in the horizontal axis, lambda in the vertical axis. What I'm showing that for any lambda between 0 and 1 here, if p is small enough, so attached to the vertical axis, I get this, I prove this blue region, which is only FP1 survives. That's what we show. No, not working.
I just have a quick question. So this result would correspond to the first simulation that you showed.
That's right.
But it seems like a little bit counterintuitive because in the first simulation, it seems like there are a lot of FPP lambda.
Yes. Well, yeah.
Yeah.
So you could decrease P even further in that simulation, right?
Oh, okay.
So the simulation, of course, I tuned P so that the picture looks nice, but you could decrease P further and you get more and more pronounced that the type 1 goes around regions. But still, even if P is smaller, as long as you have one seed that does something, you see these big macroscopic regions occupied by type 2.
Okay, thank you.
Yeah. No questions? No? Okay. So what we expect is that we can, okay, before what we expect, let me say the other regimes that we know. So if lambda is bigger than 1, because you notice that I'm asking any lambda is smaller than 1. If lambda is bigger than 1, it's easy to see that FP lambda is the only one that survives. And this is because, you know, if you go at some directions, you see eventually hitting a seed that just goes along that direction quickly, get a little bit of a distance. And since lambda is now larger than 1, it just increases this distance as time goes to a point where it can go back and encapsulate it, encapsulate FP1. So this is easy to show. It follows from known results of sparse percolation. If you are interested, I can tell you later offline. Another, the trivial case, as we already saw, to the right of one minus PC site, FP lambda is the only one to survive. And then the result leaves this region here that's unknown, this region inside this rectangle. And we expect that this region where FP1 survives could be extended all the way to 1 minus PC site. That's what we expect. And that also that the region of FP lambda being the only one to survive would enter inside this rectangle. That's what was expected and left open in the work with Vladas. And then more recently, with Tom, that's here, we showed, we kind of confirmed this conjecture. So what we did is we showed the opposite. We changed the order of the quantifiers, right? We look at for any P that's smaller than 1 minus PC site, and we show that for any P, if lambda is small, then FP1 survives. So just to confirm, I can put these two theorems side by side, and you see that it's just changing the order. Just now saying for any P, lambda is small, and before what for any lambda is small. And let's focus just on the case of FP1 survive, which is actually the interesting case when you are modeling growth process like that. Okay, so but there is a caveat here that I need to remark, is that PC site is strictly smaller than a half in dimensions 3 and higher. It's bigger than a half in dimension 2, it's 0.55, something like that, but strictly smaller than a half in dimensions 3 and higher. This means that 1 minus PC site is bigger than a half, so the interval PC site to 1 minus PC site is non-empty, so I can take a P in between. If I take a P in between, since P is smaller than 1 minus PC site, I can apply the theorem and find a lambda small such that FP1 survives. But since P is bigger than PC site, then also type 2 survives, because the seeds form a percolating set, right? From an infinite cluster by time 0. So it's kind of for free, just for FP2, for FP lambda, because for FP1, it's kind of a hard proof to do. But still, you get that coexistence in dimension 3 and higher. So the current picture is the following. So to the right of PC site up to our PC site, we have coexistence of both types. To the left, we don't know coexistence. There is a regime where only type 1 survives, but we don't know coexistence here. So it would be very interesting to kind of get a regime of coexistence to the left of PC site. In dimension 2, we don't know coexistence at all. So the gray region here just means I don't know what happens. Okay. In dimension 2, we don't know a regime of coexistence at all. It would be really, really interesting to know whether there is or there isn't coexistence. Dimension 2. Any question about the result? Okay. So let me just a quick remark that actually will show a very strong sense of coexistence. What we not only show that both types coexist, but actually both types produce a positive density. because FP lambda obviously has a positive density because the infinite class of percolation has a positive density in the density higher here. But actually, our proof also gives that FP1 occupies a set of positive density. So both types occupy a set of positive density. This is completely different from what happens in other models, if you know, like the two-type Richardson model and so on. Okay? I'm not going to mention much about that. Let me take now, I want to take 10 minutes to just tell you a little bit about how we prove this result, or a simpler version of both results. Is there questions before that? Okay, so let's try to look a little bit at the proof. I'm just going to give you a very, very rough idea. Okay, if you are interested, I would be happy to talk to you more offline. But the proof is quite involved. It's multi-scale analysis with even some novel ingredients for the multi-scale analysis. So it's kind of involved to go over here. But the main, I hope to convey the main idea, especially the main ingredient, new ingredient that to add to this multi-scale analysis to make it work. And I won't require any knowledge of multi-scale analysis here, so you don't need to know anything about it. Okay, so let me look at a simpler theorem. So let's try to prove that FP1 survives with positive probability for P and lambda is small, both is small. I can take both simultaneously small. Okay. Let's try very simple. So I'm going to again tessellate. I always tessellate things in my papers. I don't know why, but let's tessellate space in sub-boxes of size L1/3. And I call it a sub-box because each sub-box will have a box around it. So this sub-box has this gray box around it of size L1, which has the sub-box in its center. So you see, this sub-box here will have also a box around it, and it will usually intersect with the gray box. So it is one. Okay. I want box to overlap a lot. And then I'm going to define box to be good or bad. According to what? Well, I want a box to be good. I want that when a box is good, it favors the event that FP1 survives. So that if I find several good boxes, FP1 is surviving. That's what I want. So a box will be good if three events happen at the same time. So first, I have no seed inside the box. So the box is free of seed. Then I want that the passage time of FP1 to go between any two sites in the box, say from here to here, just as of the order of the L1 distance of these two sites for all pair of sites in the box. No, I can do this. I have concentration of passage times, so I can do that. So I want the passage times to be of order, let's say L1, right, the size of the box. And third, I want the passage times of the second type to be very large, actually bigger than L1 squared. And notice that in my regime of small p and lambda, I can make these three events be likely because I can first take L1 large enough so that the box is so large that passage times of FP1 concentrate. This depends on no parameter. Right? I just take L1 to be large so that the passage times concentrate and I can show event 2. Then after fixing L1, I take P small so that the seeds do not appear inside the box of size L1. Sorry?
The unoccupied seeds do not appear with.
It means that at time 0, there are no seeds inside. So this happens with probability 1 minus P to L1 to the D. So if P is small, I can make this event likely. That's the thing. And then I can make the third event likely by taking lambda small. Because if I take lambda very small, I can take that the passage times of each, this is a passage time of each edge inside the box. It has to be at least L1 squared. After I fix L1, I can take the lambda small so that this is likely. Then what I get from a good box, I get that if I'm lucky enough to see first passage FP1 to be the first type to enter this box, suppose it enters from here, it's the first one to just step on the box, then FP1 can go anywhere in the box because there is no seed inside. It takes type L1 to go between any 2 points in this box. So in time L1, it goes everywhere in the box. And FP lambda has no time to step inside. because even if it gets to the boundary from outside, it cannot jump inside because this takes time L1 square. Okay? So if I have a good box, it's completely taken by FP1. And since box overlap, like this two box, it gets FP1 to the neighboring box and I can make it spread. So I'm very happy if I get a good box. Right? But there's a really huge problem here. Don't read this guy. The huge problem is that everything was conditional on this, that I wanted FP1 to enter the box first. So the event whether the box is good or bad is a local event. You see, it just depends on the seeds inside, on the passage times inside the box, and again, passage times of the other type inside the box. It's really an event that's local. These joint boxes are even independent. It's really as great a process as I can always expect. But I can only use the goodness of the box if I knew that FP1 enters the box first, because if I don't know this, maybe the box will be completely ruined, would be completely taken by FP lambda if FP lambda gets there very early in time. Right? And this event depends on the whole history of the process. It's highly non-local. So the main ingredient that I'm going to add and that I want to talk here is how to handle this, or how did we handle this? And hopefully this can also find applications in other models. So just to conclude, in this slide, I have still one more slide at least. The event that a box is good is easy to control. It's independent for this joint box. So I can easily control where bad boxes are. Right? This is boundary dependence. If you know there is ligature space, it is stochastic dominates independent percolation. I can really know everything about where bad boxes are.
So in point 2, it says the time FPP1 takes to go between any two sites is fast. That's not necessarily depending just on the, say, the sites in the box. It could go outside and wouldn't be independent.
Yes, I was not precise here. What I mean by this event is restricted to this to the edges inside the box. That's important. Any more questions at this point? So let's see how we handle these non-local events. So we know that good and bad box, we know how to do it. So the way you handle it is by taking each good box and further classifying it. I'm going to classify it in either of a box of positive feedback or negative feedback. And for short, I'm going to just call this positive or negative. Bad box are not further classified. They are just bad. I don't want to touch them. So now, how do we define a positive feedback box? So our box is going to be positive if that non-local event happens, if FP1 is the type that enters the box first. And now you should be all disappointed because it sounds like I just renamed the problem, just calling the problem positive feedback. Right? That's right, but the reason why we call it from a different name is that we are going to approach this different. Okay, so for good and bad box, what do? We dissect the box. We dissect the box, look at the passage of time and say, oh, this is good, this is bad. I can estimate the probability of being good, being bad. For the feedback, I'm not going to do that. I'm not going to look at the box and see whether it's positive or negative feedback. No, I'm going to take this information for granted. It's like a higher entity just gives me which box are of positive and negative. And then I'm going to assess the consequence of that. I'm going to see and say, oh, this is possible. Actually, this is not possible. Okay. It sounds funny. It sounds like I'm not doing anything. But actually, everything hinges on the definition of positive feedback. And here I'm giving you just a very simple example. Right? The definition is a little bit more complicated than this. And it's in a multi-scale fashion. But just to give you an idea, everything hinges on the definition. And we juice out consequence from the definition. That's what we do. So let me tell you one thing that's the important thing. Oh, that's why we call it a feedback, because we don't analyze it. We take it as information that's given to us. Just, I want to give one thing, and that's the last part of that's point of my talk. It's the main property. We juice out several properties of a proper definition of positive and negative, but there is one property that's key. The others are also important, but this one is key and can be seen even in this simpler definition. And it's the following. Suppose I have a negative box here. So negative boxes are good, remember. Right? Good, only good boxes are classified as positive and negative. So this is good box. Negative. Look at the site that was entered first. Suppose it's this site. It's certainly entered by FP lambda because it's a negative box. Now, these sites are the boundary of the box. So it belongs to a sub-box. And this sub-box has its own box, right? So it's at the sub-box of some box. Suppose it's this one. It has to be different than the original box. I call this box the parent of that box, right? Note that the entrance time of this box occurs before that box because this point is at the center of this purple box, right? So it must have entered before. So parents, we're moving back in time if you go from a box to its parent. What I claim is that this purple box cannot be positive. Why? Because it's FP lambda that did this. If it was positive, FP1 would take the whole box. That's what we saw in the first slide of the proof. So it cannot be positive, it's negative or bad, could be bad. But if this one is negative, well, it will have its own parent that again cannot be positive. And if that one is negative, it has its own parent, which again cannot be positive. So I can keep this path of parents, which cannot close a cycle because I'm always moving back in time. So it has to end in a bad box. And from other properties that I'm not going to have time to go into, we can actually show that this path cannot be long. Now, each path kind of incurs a penalty in the time, so it cannot be very long. So this means that that negative box will be around bad box. But bad box, I know where they are because of the whole approach that I mentioned before. It's a local event. So funny enough, by a proper definition of what positive means, I managed to control where all negative boxes can ever be. Sounds like black magic. It still feels like black magic, to be sincere, but it really hinges on the definition and juicing out some properties from this definition. Okay? So I'm gonna actually stop here because I don't have much time. So the proof just finished by, once you know where bad boxes are, and you know the negative box has to be around it, I will do a multi-scale analysis to show that the positive box really form a strongly supercritical percolation, and in this box, FP1 just conquers everything, so they conquer a huge amount of space, they survive, they have a density and everything. Okay? So if I finish here, I'd be happy to talk more about this offline if you're interested, but I thank you for your attention.
Further questions for Alexandre? Or in the chat, maybe?
Where are these negative good boxes, actually, negative feedback good boxes actually? How is the, I mean, like, what is the density of them in some sense?
I cannot give you the density of negative box. I can give you some upper bound of the density of negative box. Because I don't know where they are. See, I don't look at them. I just bound where they could ever be. That's the way that we can do. So I can give an upper bound of the density of negative boxes. Yes.
So the time penalty that you said associated with this chain of negative feedback boxes, does it follow directly from the slow rate of FP lambda?
So I didn't understand the beginning.
The time penalty that you said,
yes.
Is it directly following from the slow rate of FP lambda?
It does follow from the fact that FP lambda is much slower, yeah, but it's more involved than that. I mean, it really, you have to analyze what happens if you have a negative box with a negative parent, and you want to see, and essentially all the proofs in the paper go by either induction or how do I call it? I forgot. Contradiction. So you just go for contradiction. If I have a negative feedback box and a negative feedback parent, how could their entrance time be quicker? Because to be quicker, it needs that FP1 did something, because they are good boxes, right? And it's doing FP1 something that it cannot happen, because then it would make the box a positive. That's essentially what would, but again, it's difficult to say without properly defining what these things are.
Thank you.
Any final questions? If not, let's thank Alexandre again.
Thank you.